Okay, perfect. Recording has started. So today we have to discuss about this constant force of mortality assumption for the fractional ages, and then we will proceed to the remaining two topics of the lecture. So yeah, then we can start by the assumption. I think that Adobe is bit slow to respond. Now it's working. So under the fractional ages, we discuss how we can calculate these death and survival probabilities and also the survival numbers and eventually the death numbers we can calculate for a given decimal time in terms of years. So we calculated these current random, or which was our current future lifetime random variable is an integer random variable. And the it's denoted by the capital Kx, and Tx is a continuous random variable. So we use Tx to create the Kx, and still we can use this Tx and its properties to calculate fractional ages. And we used an assumption at that case as the uniform distribution of death. And we showed that we can stick into uh, the death probabilities at a fractional age, which is between 0 and 1, denoted by R. And we can find it by just multiplying the annual probability, which is the subject is at age X, and we are finding the probability of death occur during the next point R, or let's say it's like zero point 0.5 years or in 6 months. So then R become zero point 0.5. If it is 9 months, so then it's 9 over 12. You can get this as 3 over 4 and put it as a decimal number. And then you just need to multiply that decimal number with that annual death probability. So we can linearly interpolate in between the survival numbers if we had the number of survivors at age X and number of survivors at age X plus 1. And then we move to discuss different examples where we discuss about finding these linear interpolated values of the number of survivors. And also we could find the fractional probabilities for the death and also for the survivor using this notation. And at some points, we had to use the complement rule, which is the death probability plus the survival probability is equal to 1 for a given year, to distinguish between uh, these fractional age assumptions, because under the UDD, we can only multiply the fractional, the probability or the annual probability of death by the fraction. So if you need to find the survival probability, so you should convert it to the death probability first and apply the rule and then convert it back to the survival probability. So that was our uh, practice. And then we discuss uh, how under this UDD, or the uniform death distribution assumption, we could find this density function. If you could remember, so we had um, a formula to calculate the density function of the future random variable as the force of mortality times survival probability. But in here, since the distribution is uniform, we could find it uh, using the annual death probability. Um, let's write down it first. So, so now since if the distribution like quickly clean this mess and proceed to there. So since the distribution is uniform, we could get the density as the death probability for the entire year, which is a constant during that year. So the same thing happens in here. And since we could use the same principle for the previous equation we knew, so we could find the force of mortality using the first density function we defined, which is the annual death probability over the annual survival probability for the period we consider. As I mentioned, since we are applying this UDD assumption for the death probability, so we use 1 minus R times the annual probability by applying that slope. So that is the interpretation there. Now we move to the constant force of mortality assumption. So by its name, it sounds like we consider this mu x plus r as a constant. So previously the distribution or the density was a constant. We know when for the uniform distribution, if we say we have a uniform distribution in between A and B, we have A and B, we have a density which is equal to a constant level in between A and B, and for the every other region or the throughout the X, we don't have any density. So the height is 1 over B minus A. So that is the density of a uniform distribution. So in that case, the density was a constant. But now the force of mortality is a constant. And we say that when this fraction is in between 0 and 1, so we can let that constant uh, be like mu bar, or even it's the for the simplicity, we can set it to mu. And then we know that we get this equation where we could find the probability of a person who is at age X surviving for 1 year is equal to the integration from 1 to 0 to 1, and we need mu x plus u to be integrated in this region. And now if this is a constant, as we have specified in here, let's say it's mu bar, so we can take it out, and the integration of 1 in this region is also 1. That means we get the constant like this. And we need to like let it be, so in this integral has to be a negative value, and it should be, so I'll write it clearly this side. So to find this, we wanted, so this equation, and in here t is 1. So to find this, we can have this directly. This is a constant. That means it gives this. So that is how we can define this probability. And I mentioned that we don't need 1 if it is 1 year, so we can omit that one. from the left-hand side. And this is the transformation from exponents to natural log. So it says, under the constant force of mortality, we modify the survival probability. So that is the difference. So under the UDD, we modify the death probability. Under the constant force of mortality, we modify the survival probability. So we can now prove this equation here, which is, it says, so when there's a remaining fractional age, which is the R, and we get the power of that annual probability with respect to R. So that is the application there. If I could write down this probability using the life table functions, it says, suppose for instance, we could get rid of U and just think about, we have a person at age X and they are surviving for point R years, which means it can be any number in between 0 and 1. And to get the probability, we have to divide it by the current number of survivors. So this is the probability that person at age X surviving for next fractional array. So using this equation 6, we can say the same probability should be x plus 1 over x to the power r. And if you distribute this one, you will get, that means first take the log from both sides, and then you have log of this and log of this. Then you have r time log of this minus log of this. Then when you simplify it for log of L x plus r, you get this. So that is just a transformation of this probability. And it's a linear interpolation. So we had something similar to this when we were here. But in that case, we used Lx and Lx plus 1 directly under the UDD, or the uniform distribution of death assumption, like in here. But when it comes to the constant force of mortality, so we interpolate the number of survivors at an age X and X plus R after taking the log value of that one. So that is the main difference in between these two assumptions. And now you have two differences. First, under the constant force of mortality, we modify the survival probability for that year, and we use the number of survivors after taking to the log scale to linearly interpolate the values in between x and x plus 1. But when we were using the uniform death distribution assumption, we modified the death probability, which is Qx, and used the number of survivors at hx and x plus 1 as it is for the linear interpolation. So those are the two cases we can use, which means we can think about when we are dealing with the constant force of mortality assumption for fractional ages. So without taking much time, we can go to this example and discuss it further so that it will be clear to apply, and we can do some calculations using these to make sure we understand the concept. So in here, we are given the following table where we have ages from 60 to 65, and we have the number of survivals and the number of deaths. And assuming the uniform deaths between integral ages, we need to find these three probabilities, and we calculated it separately. In here for the UDD. So you can do the same calculation since we have the answers and the procedures. So you can do the calculations using these two new equations for this question. Since we have like tried it earlier, I'll just mention the steps and we can like quickly go through the question and move on to the new question. So as we discussed in the last week, whenever you see a probability to calculate, so you can apply the corresponding equation we have derived directly. And in here, so I change, first I'll change these values. So we edited these linear ones to be the probabilities so that we can do some more calculations. So instead of these linear interpolations, I convert it to the death probabilities from 60 to 2.2 more years and 62.8 to 0.3 more years. So you can use those two, and also applying the linear interpolation is somewhat easy, and you can do that one later as well. So let's solve for part A first. And in here, unlike in the UDD assumption, which directly modifies the death probability, if you are using the constant force of mortality, so now it is not uniform distribution, it's constant force of mortality, and we could only modify the survival probability. That means we can write down this probability or the required probability using the survival probability. Now we can apply this equation to the survival probability directly, where we say P61 to the power 0.2 because of the sixth equation. So to find this survival probability of a person who is at age 61 for the next year, we can use this table where usually we say x plus 1 is 60 plus 1, which means 61 plus 1, and divided by Lx, and we take it to this. So you can submit, which means substitute these two values, this one and this one from the table to here, and find this probability. And for part B, we were asked to find the probability from 60 to 2.2. So I edited this question because finding L, which means the number of survival, is quite straightforward by using these values, substituting the values by using the values in the table. So that's why I make it to a probability, which involves some more calculations. So for this one, it's 60 and going for 2.2 more years. And For this one, again, R is a fraction. So within the 2.2, we have two complete years and zero point 0.2 as the fractional age. So to remove that two complete years from this equation, we can reform the equation like this. This person can survive from 60 to 62, which means 2 more years. After that, they can survive the next 0.2 years, which means now that person has survived 62 years and only has to survive 0.2 more years. So this is the point where we can apply the fractional age correction. And for this one, L60 plus 2 divided by L60. And for this one, it's a fractional age and it's P62.2. And again, for this, it's L62.1 divided by L62. So now we can substitute these two numbers from the table and these two numbers from the table. So we'll get this probability directly. And finally, as the last day, we can find this probability instead of the linear interpolation, 60.2, the next 0.3 years. Let's use part C in here. And we need to find the death probability of a person who is at age 60.8, 62.8, and the death occurs within the next 0.3 years. And now, so we need this, but to get that one, if we use the complement rule, so we will find this first. So for the survival probability, we can decode this again like we did in the last week. So as mentioned, if this R and 0.8 is U or S. So if you sum up those two values and if you get more than one for that summation, that means you have a complete year and some remaining part of the fractional age. So we can distribute it like this. First, we want this 62.8 and we to complete it for the whole year, the complete year, it's 0.2 more years, like 60 point, surviving from 62.8 to 0.2 more years. And we have one more, one, which means for the remaining time, we have 0.1 more remaining years. To do that, so we can get this one. Now we have 63 and the remaining years are only 0.1 because we have consumed 0.2 for this one. So unlike under the UDD assumption, so this one is quite comfortable because we are directly using the survival probability itself. And using the independent law, we start from 62.8 and go for the next complete year, which is 63, by adding 0.2 more years. After that, they have survived for 63 years, and we only need to go 0.1 more year. So now it's easy because in the equation 6, it's mentioned if this R plus U is less than or equal to 1, you can apply this directly, no matter what the value of U. So the value of u is 8, but r is 2 here. So we can neglect the 0.2 or 0.8 and use the 0.2. That means the same probability can be calculated using these two probabilities now. And to get it, we can use table values directly, and it gives the answer like this. So once you find this value, you just need to subtract that from 1 to get the required death probability. So that is how we can continue to find this one. So if you were asked to find the linearly interpolated value of the number of survivals, you just need to use these L's directly from the table and derive the fractional age. So that means if I visualize it, it's like this. So you have x here, x plus 1 here, and your r is somewhere in here. So what you do is this cap is r, and this cap is 1 minus r. So you are multiplying the Lx in here with the remaining cap. So Lx should be scaled to a natural log scale. And here we have Lx plus 1. So it is the log value of this one is multiplied with this fractional age r. It will give the value at age x plus r. So that is the pattern we can recognize in this multiplication. So now we can go for the next example, which use a different life table with a small number of observations, and it contains some life table functions as well, because we first need to find the value of C1 and C2 and then use the values to get these unknown probabilities in the remaining parts. So to find the value of C1 and C2, we need to stick to the fundamentals of the life table, where I mentioned that dx is the number of deaths within that year. So the difference in between two successive LXs gives the death of the previous year, which means the difference between L92 and L93 is this D92. So you can see if you subtract 900 from 840, you will get 60. So that is the number of deaths during the 92 cohort. And in the same way, so you can define two equations for C1 and C2. Here we can first write down Lx at 93 is this, and Lx at 94 is unknown, which is C2. And this difference is the number of deaths in the 93 row, which is D93. And it is also unknown, and it gives one equation. And for the next two rows, the value in C2 minus the number of survivals at the beginning of 95 should be equal to the deaths during the 94, which is 70. And that is the second equation. And from the second equation, we can get C2 as 770. Then eventually we get C1 as 70. So now you can understand it's just a simple math. So in each row, for dx, it is the remaining Lx and the next, or the difference between the remaining Lx and the next Lx in the table. And eventually dx goes to the final value, and at the limiting age, both Lx and Dx should equal, because after the limiting age, there's no survivors in the population. So we have to calculate these probabilities assuming the uniform distribution of death between the integers. That means the UDD assumption. So for UDD, we know we have to modify the death probability, not the survival probability. And we are asked to find the survival probability first. So, and it is a fractional age, but with the whole year inside it. So first we need to do is separate this complete year from this fractional age and write down it as a multiplication of two independent probabilities, which is surviving from 90 to 1.4 more years is same as surviving from 90 to 1 and 91 to 0.4 more years. Now, we can get the survival probability from 90 to 1 more year is L91 over L90. And for this one, we can apply the UDD assumption correction directly like this. And it's 91 here. So for this one, since we have the D values, we don't need to use this complement rule again. We can use the deaths and directly apply this one. So L91 is 950, L90 is 1000. And for here, we have the death probabilities at 91 means number of deaths during the 91 year and the number of survivors at the beginning of the 91. So here we can use the usual notation and write down it first. Deaths during the year 91 and number of survivors at the beginning of the year 91. And you can get it from the table. And it's 50 over this. So once we simplify, we get the corresponding probability, which is the survival probability of a person who is at age 90 and surviving for 1.4 more years. That means the age by the end of the survival period is 91.4 years, and it's 0.93. And since this is an example, I'll use this space for the alternative way. So in here, we use this independent assumption in between these ages, but now we can do the same thing under that assumption, but we are not going to apply these equation for Qx, but now we use the linear interpolation. So for P90, it's same. I can write down it like this. But for this one, we can write down something like this. So this is L91 plus 0.4 divided by L91. And from the fractional age, we know that we can write down this linear interpolation case. So since R is 0.4, we can write down R times X plus 1. So X is 91 here. That means 91 plus 1. And 1 minus R is 0.6. So at that time, it's 91. And we can cancel out these L91s from there. So we directly get the probability using this. Still, we don't need the death count at each year. We only use the three different number of survivors at each year. So this is also giving the same required probability. So that is the alternative way. So now we can see it's possible to get the answer using both equations, but depending on the method you choose, take some time to go to the final answer. So if you use the first method, it takes some time because we are dealing with different probabilities at different stages. But if you use the linear interpolation in this time, it's just 2 rows to get the answer. And for the part C, now we are repeating part B by assuming the constant force of motility. So under the constant force of motility, we directly modify the survival probability. That means we can first apply the distribution of these ages in between 90 to 91 and 91 to 0.4, assuming this independent assumption. And after that, P90 to 91 is pretty much the same quantity we need to calculate. And for this one, it's P91 and to the 0.4. This one was 0.95 from the part B. And for this one, we can set it like L92 divided by L91 to the power 0.4 and gives 5 times 900 divided by 950 to the 0.4, which is equal to 0.9296. So now we see that two assumptions depend on different set values. So if we ask to use the UDD assumption, that means we are going to modify the death probability. And if we are asked to use the constant force of mortality assumption for the fractional age, that means we are required to use the modification of the survival probability. And eventually we can use the two linear interpolations. But for the linear interpolation under UDD, it directly use the number of survivors at linear ages in between x and x plus 1. But for the constant force of mortality assumption, we have to use the log scaled Lx and Lx plus 1 for the linear interpolation, but the pattern is clear. R minus 1 is multiplied by the number of survivors at age x, or the log value of number of survivors at age x, and R is multiplied by the number of survivors at age x plus 1, or the log value of the number of survivors at age x plus 1. So that is the story for the fractional age. And now we need to move to the select an ultimate tables. So before that, I'll summarize these three quantities under the UDD and the constant force of mortality assumption for fractional ages. So we know that we need to calculate the probabilities of survival from x to the fractional age, and the death probability in between x and the next fractional age, and the force of mortality. So these three quantities under UDD assumption and the constant force of mortality assumption behave in different ways. So under the UDD, we modify Q, or the death probability, so that whenever we want to calculate the survival probability, we transform it to the death probability term and apply the transformation. But under the constant force of mortality, we need the survival probability only, modify it like this. And under the UDD, it's directly converting the form into the fractional. Using the fractional equation, we can convert this form by multiplying the fraction by the annual death probability. But under the constant force of mortality, we modify the survival probability. That means we convert it into the survival form and then apply the relationship. So that is how it works. And under the uniform distribution of death, we know that the density function is a constant in between x and x plus 1. That gives us the force of mortality as this. And under the constant force of mortality, this one is constant, which means mu x, so the force of mortality is constant. That means we know that this one is equal to this. Using that, we can get the log value of p x as mu x. So those are the things we need to summarize from this subtopic, which is the two assumptions of the fractional age distributions in between two integer ages. So now we are going to select an ultimate topic. As I mentioned in the beginning, so we had these ultimate tables. That means it contains the information about the number of survivals and number of deaths. And also I mentioned that in these tables, we have probabilities and expected values, which we are going to calculate in future. There are some tables, even in the exam, we provide those kind of table, which contains the calculated probabilities as well. So, but for all these cases, the numbers representing at each column gives the corresponding value for the age at each row. So like in here, it says, in here, it says at age 90, the number of survivals who are entering to the 90th year of their, after completing 90 years of their age, there are 1,000 candidates who are entering to their 91st year. And out of that, 50 will die. So that is the story in this ultimate table. And the select term emphasizing here that, so due to some research, so when we are going to provide an insurance to a customer, we can say different customers carries different type of life conditions, and depending on their job or depending on their proximity of living, or depending on their different types of daily habits, the mortality can be changed. So, for an example, if someone is traveling to Colombo daily using a motorcycle, has a different like the probability of death, than someone who is traveling by bus and train. And it is more different for a person who is traveling uh, by a large vehicle or just to the uh, walking from home to the office. So that's the common ground. But even from that cohort, if someone is like doing some hobbies or going fishing or do mountain climbing or waterfall trekking, so then they are adding some more uh, like events that increases the death probability or the possibilities of death for that person. So then, uh, when you are going to buy the insurance contract, the insurer considers these cases and say, though you have the same age as someone is not as risky as you. Suppose someone is working from home and he's not traveling daily to the office or even for the supermarket. So he's something like his movements are restricted to a certain area, and that means the life-threatening dangers are limited for that kind of a person compared to a person who is traveling daily and spending more time on the road during the peak hours, that means morning and the evening. And then the insurer will think that, so if both are having the same age, say 35 years, so then the person who work from home has a less probability of having a death causing injury or death causing incident than the person who has a more traveling uh, habit. So in that case, we can consider that even though they are having the same age, like 35, for an example, we can consider the person who is at home is in the general ultimate table, and he has all the values corresponding to the 35th row. But for the person who has more dangerous behavior habit, like traveling in peak times and going for mountain climbings, then we add the 2 or 3 more years depending on the past data and consider that person as a person who is at age 37 or 38. So that means we have selected that person. So we know that for the survival function, it's a decreasing function, and the survival probability of a age at uh, the person who is at age 37 is less than the survival probability of a person who is at age 35. That means even though they have the same age, we considered one of them as more older than the other one because of their dangerous habits. So in that case, the selected person is the person who has the dangerous habit, and the person who's going with the ultimate table is the person who has the general habit. So in our case, the person who is not working from home goes with the ultimate table, but the person who travels to the workplace goes with the and also having some riskier hobbies like mountain climbing and waterfall trekking. So that person goes for the selected table. So that's the basic description I can explain in this topic. So that story is given in this first point, and to indicate that this life is selected, we use this bracket. Uh, we take it like in the parentheses, we write down the age. So if you see a person with the probability like this, it says the probability of a person who is at age X surviving for next year. But if you select or the see a probability like this, it says the probability of a person who is at selected age of X and surviving for next 3 years. This indicates this person is a selected life, and the selected time period should be given to you, and you can calculate those probabilities. So these two probabilities are not same, even though they are in the same age. In our example, we took 35. So that means, let's say this is 10. So this is not equal to this. So they are in the same age. This right-hand side person is a selected life, but this is an ultimate life. So to distinguish in between these two cases, so we use this notation. And then if we are going to the age 36, which means x plus 1. So in that case, we only add 1 out of the bracket. It indicates the selected age is x, but now that person has already survived one more year. So X is kind of the selection occurs when they buy the insurance. That means the value inside the bracket says that person purchased this insurance at this age X. So in this example, suppose these two are friends and came to the company and they brought this insurance policy at the age of 35. And now they are 36-year-old. And then I can say in the next year, again, if I want to have the remaining probability, then I can write it down like this. 35, the selected age, plus 1, and remaining time is 9 years. So the inequality holds, and the selected age is there until the selected period is over. So in here, so we call this process as the underwriting. And as I mentioned, the survival or the uh, after the selected period, we can say these two probabilities come up to uh, the same value. So in the definition, I mentioned that the selection period only goes for uh, some predefined years. So after that, if you feel like there's no additional risk of this life compared to the ultimate life, then we consider that after these selected periods, both probabilities are same. So during the selection period, it's not same, but after the selected period, the selection effect is not there. So you can say it's same. And we can create, like using the ultimate table, we can create the selected and ultimate table for different cases where it contains both ultimate and selected probabilities. So we should like uh, recognize how to read that table, because it's not simple as reading the ultimate table, because in the ultimate table we just need to refer the row and the column, then the intersection of that row and column gives the corresponding value of that column corresponding to the age of that row. But in here it's a different method. So we can uh, try that method in this example. So I have two more points to discuss before the example. And yes, I mentioned that this process is called the underwriting, and the effect which cause these probabilities to um, like have two separate values. Um, we call that effect as the underwriting effect. So, and yeah, so the third point says that the QX is the probability that the life uh, at age X now dies before the X plus 1 year, which means because QX and goes to one more year. And then since there's a bracket, we can say the life is a selected life at age X, and the effect of underwriting appears to during the selection period. In this case, we don't know, but suppose it's for n years. So then after that which means after the selected period of n, both the selected death probability and the ultimate death probabilities are same. It's like this. Uh, when we are going back to the example we had, those two friends bought the same insurance policy, and one life was a selected life because of those dangerous habits. But after 3 years, company when the renewal occurs, company recognize uh, that the life was like behaving as the same ordinary life, which has the ultimate probabilities, and they can say our selection period is should only goes up to 3 years. After that, the selected life will be considered as the ultimate life after that. So even though that person had the riskier travel behaviors and also hobbies, the company will like depending on their do they have the same policies, depending on their uh, amount of benefit and also the other type of facilities provided for them through the contract, uh, they will pay different premiums, and the riskier life sometimes may pay some slightly higher premium than the less riskier life. And in that case, company can like predict the selected period and say after this, in this example, after 3 years. So they says that after 3 years, we don't have kind of extra risk of carrying this life into our insured pool, because if there's something to happen to that life, it will occur during the next 3 years with that highest probability. That's why we selected the life for only for 3 years. And after that, we consider that these kind of risky behaviors are not causing any additional probability of death. So that's the kind of the general interpretation I can give for that example. And then we can say, like I mentioned, so we have during the selected period, these two probabilities are not same. That means we can calculate an index to measure the effect of underwriting. So we can indicate it like capital I and X to the K, like X is the age of selection and K is the period. So this is one way we can, the one such statistic that we can use to measure the effect of underwriting in different years and uh, decide whether we should like extend the underwriting period or limited the underwrite period depending on this index. So you can see it's 1 minus the selected probability over the ultimate probability. And if this ratio is equal to 1, that means the index should goes to 0. So this ratio is equal to 1 if the selected probability and the ultimate probabilities are same. So this occurs after the selection period. So that's how we defined it. But before the selection period, it's always in between 0 and 1. So if it is 1, the index is 1, that means the ratio is closer to 0. And the ratio can go closer to 0 if this selected probability is closer to 0. That means uh, we can measure the effect of this underwriting selection decision by calculating these selected probabilities and the ultimate probability for the same year. And this bracket only indicates the time of the selection happens. And then we can move to this example to apply this one and test how to read this uh, table. So as I mentioned, so now you can see it's not somewhat similar table as an ultimate table. So in this table, we have the probabilities as columns with the selection indicator, the box bracket, and at the final column, we can see it's like x plus 3. So in this kind of notation says, so age is uh, x, and after 3 years, the effect is not uh, valid. So that means now you can see, um, so if the person is selected at age x, so uh, we say the death probability is Qx. And if the age is 60, so then Q60 is the first selection, the probability of death at the age of selection. And then we move one more year ahead. It's x plus 1 now, which is 61, and then 62. Now we have passed from 60 to 61 and 61 to 62. And once you get from 62 to 63, selection is over. And your customers, like if we get a customer at age 60, so after the age of 63, the selection effect is, or the underwriting effect goes to 0, and the death probability at age 63 is same for the selected life and the ultimate life at that time. So that means we read it across the row and then go downwards from there. So the first column is to identify the selected age, but after that, by moving through the selection period, then we are starting from the last column and go down. So that is how we can read these selected and ultimate tables in this manner. So in this example, so they are given the ultimate and selected mortality table for 3 year selection period. And as the first part, we need to calculate the probability for this person who's newly selected at this age. Let's say they are given a date and they have given that after 1 year, the age is 61. That means the age when the policy was offered was 60. And we need to find the P on the 1st of January. And the period goes from January 2001 to January 2006, which means we have to have few more jumps. And it's greater, the jumps are greater than 3 years. That means we have to cover through the um, selected period and then go through the ultimate probabilities. So let's say it like this. At age, so in 2000, at age 60, and 2001, it's age 61. And then 62, 63, 64, 65, and 66. So this is the point where selected, and now we need to calculate the probability which is equal to P starting from 2001, which is the age is 61. But I mentioned that if that person was selected at age X, so we should first write down the selected age. So this person was selected at age 60, which is 2000, and now he's 60 plus 1, which is 61. And then from 2001 to 2006, we have 5 jumps. And that means 5 complete years. Since this selection occurs in here, so we cannot apply uh, the ultimate life table functions directly. So we need to go through each year separately. So starting from 61, we go 1 year. And after that, that person has survived 2 years now. And then 3 years. But in this table and also in the question, they have given that the selection uh, period is only for 3 years. That means this is not available. So from this point onwards, it is same as this. So these are the two probabilities we should extract from the selection part, and then we are moved to the ultimate part after that. So then first I will write down all the charms like this, and this is also after the selection period. So this is same as 64, and this is same as 65. And for this one, the table is given in the death probability. These are survival probabilities. So we will write down for this part, it's Q 60 plus 1, Q 60 plus 2. After that, these are normal probabilities, 63, 64, and 65. So these two are taken from here. So the person is selected at age 60. That means we are referring to the row of 60. And this is the 2. So this is the column. We need to get the first value, and this is the column and cell. We need to get the second value. So we are getting these two in here. And after that, Q plus 3 is in the next column, and which is age 63. And at age 64, we have this. And age 65, we have this. So now you can see we went first horizontally and then going back to vertical reference. So this gives us the value of P. So that's how we can refer these probability tables. And this can apply, this can apply along with the number of survivors as well. That means LX. So the same notation, we use the box brackets to indicate the selected age, and the pattern goes in the similar way. Let's go through this example quickly, where we have these selected and ultimate table, for 2 year selected period. Since it is 2 years, you can see x, lx, lx plus 1, lx plus 2, and then x plus 2 gives you the reference for the ultimate ages. So we are asked to calculate Q, that is the death probability for the person who is selected at age 31 and death occurs within the next 2 years. So how can we approach this? Since the selected age is 31, so first we refer the 31st row. And we need the death probability, but we have the number of survivals. That means we need to convert it into the survival probability, because we can then apply the right table functions. And for this one, it's L31 selected and for 2 more years, and L31 selected. That means L31 is in here, and L31 plus 2 is in here, which is the ultimate 33. So now we can quickly substitute these two values and get this probability quick. And for part B, it says the life was selected at age 30, but now they have already survived 1 more year. The actual age is 31, but the notation says selected at 30 and survived 1 more year. And we need them to survive 2 more years. And the probability they actually gives us 30 plus 3 divided by 30 plus 1. And the selection period is only for 2 years. So 30 plus 3 is same as, so in here it's like, we don't need like, so we have already, we have already circled it, and it's the number of survivals at age 33. So we know that value. And for this one, it's selected age is 30, and we are going for 30 plus 1, which is in here. And it is this. And for part C, now it's a deferred death probability, where the selection occurs at age 31, and they have survived for 1 more year after the selection. And then the actual age is 32. They survive for 1 more years, and death occurs within the next 2 years. So if I go through the ages like this, so the selection occurs in here. Now they are in here, which is 32, and they survive for 1 more year, 33, and death occurs within the next 2 years. So if I like decode it like this, the insurance was purchased in here, and they have survived 1 year. They need to survive 1 more year. After that, the death, we need the probability of occurring death in between 32 and 35. So that means, so this is a deferred probability, and we can directly find the deferred probability using the notation of the number of survivals. We know that the number of survivals decrease with the time. And here, so the selected age is this one, and now they are +1. And we need one more year to survive. And that is the number of survivals at age 33. And by the time the period over, it's 1 and 1 more year for 33, and need to add 2 more years to come to 35. And the current age is 32, which is 31 plus 1. So this is 31 plus 2, so which is given in here, and age is 35, that is in here, and 31 plus 1 is in here. So we get the probability directly from there. So now you can see it's like not directly reading through horizontally. So we need to go horizontally until we cover the entire selected period. Then we will go vertically after that by matching the ages from the final column. And now we can move to a different example. It says, so now we don't have a table, but they have given some values of these selected probabilities. So for a 2-year select and ultimate mortality model, so we are given that the person who selected at age X and survived for 1 more year can be taken as 90 or 90%, 95% of the probability of the ultimate probability. So this is the selected probability, and selected probability is equal to the 95% of the ultimate probability of the next year. So if I draw this line, if the selection occurs in here, now the person is in here, and it's same, the probability which is in here after multiplying by 0.95. So Lx is given and Lx plus is given. So that means we have Lx and Lx plus 1. We need to calculate this probability. So we can get it like this. So the selection period is only for 2 years. That means at this point, the selection is over, and the selected probability is same as the ultimate probability after that. And then we can say, since we have these two, we can find the probability of death occur for a person who is at age X within the next year using this. And for this, again, we have Lx plus 1 over Lx. So using these two information, now I can find this probability, which is equal to 1 over 96,124, which means 96,124. divided by 98,153. And using the calculator, we can find it to be like 0.0206. And now we have one clue. And then we can say Q of this x plus 1 is equal to 0.95 times Qx plus 2. And then if like, so this is, if x was 70, so then Q71, and this is Q72. So let it be like this. If we have Q, for clarification, let's say we have x equals 70. So then we have Q70 and we have Q70 value, and then we need to find the Q71 value. And to do so, we have Q an equation in between Q71 71 and Q72. So that's the general implication we can get. So I think since we need two more jumps, yeah, because it's given like this. So this has to be equal to 1. Otherwise, we cannot find a relation in between these two. Let's correct this one. Yeah, the clue is like the same year probability, so which means selected probability is 95% of the same year ultimate probability. So otherwise, you can proceed with this notation. So it is like this. And now we are almost clear and say that if we had like these two together and we can say it like this. How we can interpret this one? Since I get it like this, so we have Q70 and we had L70 and L71. We use that one to find this like this, and we are asked to find the Q70 plus 1, and if we had 70, we need Q71. So, yeah, yeah, depending on this one, I think I have made a mistake in here because if I use the notation with this one, it should be like this and this. Then I can get this using this and this. Okay, now I got it. So when I developing the question, I made a mistake in the notation. So it should be like this. Um, so now it's 2 this one, and this one. I think now this should work with the notation. Let's say, um, yeah. So we have the ultimate probability of x plus 1 in here. And if we know the ultimate probability of x plus 1, we can get the ultimate probability of selected x plus 1. So just we first found the ultimate probability using the two number of survivors at age x plus 1 and x plus 2. Use those two to calculate the ultimate probability. Once you get the 95% of the ultimate probability, will give you the selected probability within this setting. So I just wanted to show you some like how we can perform a calculation if we were given the selection probability as a function of the ultimate probability and with some ultimate survival values. So that's how we can go. So please change the example values from qx plus 2 to qx plus 1 on the right hand side of the first point. And for the second and third points, it should be lx plus 1 and lx plus 2. So now that's clear, and we can proceed to the next example quickly, where we have the selected table as in a usual way, and we can say it's a 2-year selected period because we see Lx, x plus 1 and x plus 2, and the last column is x plus 2, and assume that the deaths are uniformly distributed between the integral ages. Now that means the UDD assumption. So under the UDD assumption, we modify the death probability, but now we are asked to calculate the survival probability. So you don't need that much of, so I'll write down this one clearly. 0.9 of the survival probability of a person who is at selected age 60 and surviving for 0.6 years first, and then again surviving for 0.9 years. So this is the number we need to calculate. And since we modify the death probability, so we can write down under the UDD assumption, we can write down that modification method or the linear interpolation method. And since we knew that, so it's like this, or we can interpolate it using this. So I showed that if these L values are available, it's easy to go with this linear interpolation than using um, the death probability itself. So in the table, we have the number of survivors here. That means we can get this probability directly. So what we need to do is we can say the selected probability is 60 and they have survived 0.6 times plus 0.9. That means 1.5. And then the current age is 60 plus 0.6. So these are the two values actually we need to find. Using the linear interpolation, we can do that. So let's simplify this one first. And for the numerator, it says 60. So if I can decode it like this, 1 plus zero point 0.5. So that means actually it's 0.5 fractional age problem now. So 60 plus 1 is actually 61. So, but we need to indicate the selected age. That means we can write age is 61, but selected at 60. So this is the, let's write down like this. So they were selected here, and now they are 61, and we are interested in this 0.5 jump, and this is 61, 62, this is 61 plus 1, and this is for 0.5 probability. That means it's just R equal 1 minus R. So once you decode the ages like this, so you get these two values in here. And for the denominator, it's 0.6. So we say 0.6 is the jump, and that means we need the other n value, which is here. It's a selected age plus R. So that means 60 plus 1, and here 0.5 times 60. So these four values are given in the table. Let's say 0.5 times 60 is the selected age. 60 plus 1 is in here. And plus 2 in here. And for this one, 60 plus 1 again, given in here. And 60 is in here. So we can get the final answer from this one directly. So in that example, we had a different approach because the table was given in number of survivors, in terms of number of survivors. So these three examples showed different approaches. And under this topic, it's kind of a mixture effects of applying the selected probability, but also it can be mixed with the fractional ages assumptions like we did in here. So it was a fractional age problem with the selected period, and the assumption was uniform death distribution. So anything can be mixed up with the other things, and we can have a nice problem like this. So that is how we use these assumptions and calculate the survival probabilities along with the death probabilities and the number of survivals. So if we know the number of survivals, we can find the number of deaths. So those are the things we can do when we have these numbers. And now, suppose we have the numbers, but we are not interested in a specific probability, but we need to evaluate the remaining lifetime and get an estimate of the remaining lifetime depending on their distribution. So then we need to stick to the probability fundamentals and define the movements. So we know that if we have a random variable, so we can find positive, or which means existing movements using the definition of a movement. So in here, our future random variables, they continuous or discrete depending on the type. So if we use the continuous case, so we need to get the movement, we need to get the integration with respect to the random variable and the function that we need to find the movement. If it is a curtailed random variable, which is the discrete one, so then we need to use summation in here, because we know, for an example, if x is continuous, so then the expectation of x means x times fx dx. But the lifetime is a positive measure. That's why instead of negative infinity, we start from 0. So if this was a discrete one, so then we get the summation of these values. So it goes to infinity. And here, since it is, so if in terms of the lifetime, so it starts with 0 and goes to infinity. So we can do the same, apply the same definition in here. Now our random variable is tx, and this notation, which is the expected future lifetime of a person who is at age x, and this small circle indicates it's a continuous random variable. And says, so it can take any value between 0 and infinity, and the random variable is a time, so we need t and the density function. But the density function can find the density function using these two quantities. So that's how we came up with these values. And then it's same as this. So in the probability theory, we say this is same as this. So this is the survival function. And also in our actuarial notation, this is the survival function. So we applied these two cases directly in here. We just need to adapt into the notation. And if we want to get the second movement, so it says, so I'm using these distributional theory nodes separately in here. So it says if like, or in the general case, the definition is like this. Multiply the density with x square and get the integration. So in here, it's t square and goes from 0 to positive infinity. And you can find this using this. And or you can find the same integration, the integral value, using a different integration where it involves the survival function. In this case, it says you differentiate x square, which is 2 times x now, and multiply it by this. So these two are equal. So in general, in distribution theory, we can say if we want an expectation of gx, so that means gx times fx dt or g dash, which means the first differential. You take, so differentiate gx with respect to x for one time, and then multiply it by the survival function and get the integration from 0 to positive infinity instead of this. So we use these rules to define these points. And in most cases, as I mentioned, the maximum lifetime is not infinity. So the limiting age will be omega minus x, because if we have already spent x years, so then the remaining lifetime is the maximum life minus the current age. And if we go to this random variable quickly, so it says the minimum of tx or n. That means from 0 to n, it goes as the random variable tx, but after the n, so when tx is greater than n, it always gives n. So that means something like this. If I draw, so before the n, it moves as tx, but after that, it gets the value of n. So that means it's kind of a term life uh, period. So we denote it like this. The expectation of a person who is at age x, the future lifetime random variable, but with a term n. So that means we need the actual death time only for the time period from x to x plus n. But after that, if that person survives that n years, so we don't want the death time. We just consider them as the people who have survived up to n years. So it's important in the case where we issue the term life insurance. So that's why so this is the future expected lifetime for a person who is under a insurance contract for n years. And since it is continuous, we have this circle over there. And then you can see from 0 to n, it's t times the density, and we know how to find density. And then after n to infinity, it's only n. It's a constant. And you can find these two integrals, or you can use the survival function and integrate it from 0 to n. Just a simple case. So now you will see that if you can find the survival function first, it's easy to find these movements quickly, because if you stick with the density function, sometimes you might have to do some more integrations. But if you are going with the survival function, so it's only use the range, and also it's always work with a differentiated value. That means the power is reduced by 1 for most cases. So these are the three equations we discussed for those three movements. So this is the complete future lifetime of a person who is at age X. So this we use only the survival function here because we showed that we can use the density, but it's easy to work with survival. And this is the second moment of the future lifetime random variable for the remaining life. And it's like this. And this is the future lifetime for a person for which is only considered for n year term. So then it's like this. And now we can quickly go to this example where we have given that the force of mortality is 0.01. So that means it's not a function now, it's a constant. So that it says it's a constant force of mortality at this point. And we have asked to find the complete expectation of this person first. And we know from the definition, should go from 0 to infinity since it is complete. And for the survival function, we know if we have the force of mortality, the survival function is e to the power minus the integration of this times t. And since the time limit goes from x to x plus t, so this integration goes from 0 to t. So that's how we define it. And then integrate again. So for this one, from the first part, So we will solve for the integral in the exponent, and mu x is a constant. So integration of a constant gives the constant times, and since we have limits, it's like t minus 0, and then we can simplify it to a problem like this. And for this one, it's easy to work with exponents with some constant times t, because if the random variable is t, we know that the value should get the differentiation of this times the function itself and the limits. So this will give, so at infinity, this is 0, the exponent function, because the exponential function goes like this. So at the negative infinity, the value is 0. That means 0 minus, at 0, the value is 1, and the final value is, this is equal to 100. So that's how we can solve for this. And in part B, we are asked to find the variance of dx. So this is expectation of dx. To find the variance, we need to find the second moment of dx. That means using this equation 9, it's 2 times the survival function times t. So t times the survival function is here, we found it. It's e to the power 0.01 times t and dt. And this is, so we can perform the integration by parts in here and find the value directly. And says, so if you have this one, like the random variable times an exponent, so we prefer to start the differentiation by parts using the exponent. So we keep, because in the second stage of the differentiation, we can cancel out, which means we can differentiate t and get rid of that part. So the first part says 2. So if I integrated this, then I have e to the power, so with this, and we keep t in here, and this is the first part of the integration by parts, and the second part, we keep it as it is, the first integrated one, and then we integrate this function, which is 1, and now since we have common factor, we can take this out, and for this again 0 and 1, that means 0 minus 1 for this part. But since we are multiplying with t, so when this is 1, t is 0, that means everything is 0 for this part. So we don't have to write down anything for that. So we can directly get rid of that part. And for the integration part inside here, so now it's again an integration of this exponent, which is this. And the final answer is, so for this one, we can cancel out these two, and it's 2 over 0.1 means 200. And for this one again, it's 0 for infinity. And when you substitute 0 in here, it gives you 1. Like this. And then we have as the final answer. So now we can see this is the second movement. And to get the variance of dx is expectation of dx square time minus expectation of dx to the square. So it's 20,000 minus expected value was 100 in here. That means this one. So the variance is 10,000. So that's how we can find the movements of the future lifetime random variables and then find the variance eventually. So the notation only goes for the expected values. So this is for the continuous expectation of the future lifetime random variable, and this is the continuous expectation from x to x plus n for the term life, and this is the second movement of the future lifetime continuous random variable. That's why we use these integrations there. So now we have concluded the first part of the lecture today.